Hi class, this is a video on the Bohr model of the atom. And the Bohr model of the atom is the description or model of the atom that was proposed in around 1910, a little after 1910, by Danish physicist Niels Bohr. And it improved upon previous models of the atom in the sense that it was able to account for various observations that previous models were not able to account for. And one of those observations is the spectrum of light that's emitted by gas which has been excited. So for example, here we've got hydrogen, helium, nitrogen, and so on. And what somebody has done is they've taken these gases and put them inside of a glass tube, and then they've excited these the atoms in these gases by applying a high voltage. And when you look at the light that's emitted by an excited gas, and you do that by taking the light, and you can send that either through a glass prism or through a diffraction grating to spread it into its spectrum, what you see is that these excited gases emit what's called a discrete emission line spectrum. So rather than like in a black body where a hot glowing object emits light continuously across the spectrum, when you look at the spectrum of excited gas, you see that it emits light at like this very specific wavelength of red and this very specific wavelength of light blue and this dark blue and so on. It doesn't emit light in between these wavelengths. And previous models of the atom prior to the Bohr model, they were not able to account for this. And this was well observed and studied at the time. So there's a conflict there. So here is a diagram which kind of describes the Bohr model and how it's different from previous models. As with previous models, you have a nucleus with all the positive charge and the mass at the center, and you have the electrons orbiting around it, around the nucleus. The thing that makes this model of the atom radically different from previous models is that the electrons are only allowed to be in specific quantized states, or you can call it orbits or energy levels. And so these are like the positions or the energy states of the electrons surrounding the nucleus. So previous models would allow for the electron to be in any position outside of the nucleus, but the Bohr model said it had to be in specific quantized energy states. And the Bohr model also accounts for the way that atoms interact with light. So if the electron is in one of these what are called excited states, which are these higher states, anything higher than the ground state is the one that's closest to the nucleus. If the electron is in one of these excited states, it will very quickly transition and make its way back to the ground state, and then it will stay there. And every time the electron transitions from a higher state to a lower state, and the electron can either jump to the adjacent state or it can skip it or skip two states, every time that it transitions to a lower state, it emits a photon of light, and the energy of that photon of light is equal to the difference in energy of the two states. So it's dropping from a higher energy state to a lower energy state. It uses that energy and it creates a photon, and the photon carries that energy away. Also, if the electron is in one of the lower states, it could be in the ground state or the first excited state, or one of these lower states, it can transition to a higher state, and it does that by absorbing a photon which has just the right amount of energy to boost it from a lower state to a higher state. So this is the Bohr model in a nutshell right here. It's just that you have the nucleus with the protons, and that's where most of the mass is. And then the electron, you can either have one or more electrons on the outside, but those electrons can only exist in these discrete energy states. And anytime the electron transitions up, it is absorbing a photon, and anytime the electron transitions back down to the ground state, it emits a photon. And so that's in these cartoons right here. This is showing the interaction of the atom, which is this whole bullseye-looking thing with the nucleus and the energy states. And then along comes the photon. The photon can be absorbed by the atom, causing the electron in the atom to transition to a higher state. And then the electron wants to transition back down to and make its way back down to the ground state. And every time it makes a transition, it emits a photon of light. Of particular interest to us is the hydrogen atom, for two reasons. One, the hydrogen atom is the simplest of all atoms, and it's the most well understood atom. It's just, it has a nucleus of just one proton, and then usually it just has one electron, which can transition between these states. The other reason that hydrogen is of interest to us in astronomy is it's by far the most abundant atom in the universe. So when you look out at stars and galaxies, you're primarily looking at hydrogen in terms of the matter that you're looking at, the regular matter. So with the hydrogen atom, and Niels Bohr was able to calculate this and present it with his model back in 1913, there are these sets of energy levels in the hydrogen atom. So you have the ground state. This is where the electron would want to stay. You have the first excited state, which we call the n equals 2 state. The ground state we call n equals 1. The first excited state we call n equals 2. And that state is 10.2 electron volts higher in energy than the ground state. So the ground state is 0, this is 10.2. Then you have a second excited state, which we call n equals 3, and this is 12.1 electron volts above the ground state. And the second excited state is, you do the math, this is 1.9 electron volts above the first excited state. So these two states, the first excited and the second excited, these are separated by 1.9 electron volts. And then there's more states. You have the first, second, the third excited state, n equals 4, which is 12.8 above the ground state, and so on. Remember that an electron, it can transition up to a higher excited state. It does that by absorbing a photon, and then it can transition back down to that lower state by emitting a photon. And so all of these transitions correspond to photons of particular energy. And so to calculate the wavelength that corresponds to any of these transitions, all you do is you take the difference in energy between the two states. So it could be like this one and this one, or it could be for this this guy right here, it could be this state and this state. So this corresponds to an energy difference of 1.9 electron volts, because it's 12.1 minus 10.2. Well, since you know the difference in energy between these states, you know that the photon that corresponds to this transition will have a wavelength which is calculated using Einstein's equation up here. You just plug that energy in here, 1.9 electron volts. You take the Planck constant and the speed of light, and you would calculate the wavelength. And if you do that for this transition, you would get a wavelength of 656 nanometers. Right here, 656 nanometers, and that's red light. That's this wavelength of red light. This is the color of the photon that corresponds to this transition. Now, if the electron is in the n equals 2 state, and along comes a photon of just exactly this wavelength, and which corresponds to a photon energy of 1.9 electron volts, and the electron is already in the first excited state, it can absorb that photon, that 656 nanometer photon, and it can use that energy to get bumped up to the second excited state. Once it's in the second excited state, it's either going to transition back down and re-emit a photon of that energy, or it might decide to skip the first excited state and jump straight down to the ground state, in which case it's going to take this path right here. And this would be a photon with 12.1 electron volts of energy. That would be an ultraviolet photon. So this is how the energy, all the different energy levels in the hydrogen atom correspond to all the different photons that can be either absorbed or emitted by a hydrogen atom.